All right, welcome back. So now we will continue. Let's continue our discussion on type 1 and type 2 computations. So we talked about how we can compute the type 1 and type 2 error when you have a rule given to you. And then I gave you a couple of formulas and I told you that it's a little bit abstract. So we'll today try to solve a few problems and then we'll see how to use these formulas. But before I go there, many times we're also interested in more than one rule. It might also happen that you have more than one rule, and you can use one of these one or more of these rules in combination with each other to compute the overall type 1 error probability. So for that, if you have, let's say, k rules given to you, and let's say alpha I is the type 1 error for every single rules, then you can compute the type 1 error of using a combination of these rules by using this formula, right? And then the assumption that we make here is that each of these type 1 error probabilities, alpha i's, or each of these rules, better, are independent of each other, okay? All right, now let's dive into solving a problem and see how we can use the formulas that we just studied. The question says an X bar control chart with 3 sigma control limits is used to monitor a manufacturing process. So it's given to us directly that Z alpha over 2 is equal to 3. It's a 3 sigma control chart, right? Conclusion on if the process is out of control is made based on 2 successive samples using the following rule. So now you see here, we are not just focusing on one sample, we're actually interested in 2 successive samples. And then number of samples is 4. Now you have to keep in mind this number of samples, this is n equals to 4, right? And number of samples is basically telling you what is your sample size. I should clarify here. This is the sample size, in fact. Okay, so rule 1 is if 1 or 2 sample means exceed either the upper or lower control limit, we conclude the process is out of control. That's rule number 1. Rule number 2 is if 2 sample means fall on the same side of the central line, we conclude that the process is out of control. So we have 2 rules given to us, and then we have 5 questions. The first question is, what is the type 1 error probability using rule 1 alone? Okay, so let's look at this question. For the first problem, I'm going to call this alpha 1 as type 1 error probability using rule 1. This is equal to probability that rule 1 applies given the process is truly in control. Truly in control. This is what the definition says, right? Okay. Let's now write down rule 1. Rule 1 says if 1 or more sample means exceed either the upper or lower control limit, then the process is out of control. That's the rule, right? Yes. So if 1 or more sample means exceed either the upper control limit or lower control limit, then the process is out of control. That's the rule. Given the process is in control. Okay, so far so good. Now, saying that if 1 or more sample means exceed either the upper control limit or lower control limit, I can say that this is equal to 1 minus probability none of the sample means exceed UCL or LCL. These 2 probabilities are equivalent, process in control. Now, you don't always have to do, you can still compute the probability that we have first defined, except that when you say 1 or more sample means exceed UCL or LCL, there are multiple possibilities. Maybe the first one can exceed, maybe the second one can exceed, maybe both can exceed. right? So there are three possibilities. So instead of going through three possibilities, I'm just going to say 1 minus none of the sample means exceed UCL or LCL. And in this case, I just have one possibility. And that possibility is neither X1, neither the first sample exceeds nor the second sample exceeds, right? So I'm going to rewrite this. This is equal to 1 minus probability X1 bar, which is our first sample, does not exceed UCL or LCL given the process is in control times probability that X2 also does not exceed UCL or LCL given the process is in control. Okay, now we can simplify this a little bit. X1 bar and X2 bar are identically distributed. They have the same distribution. Both of them follow normal distribution with some mean and some variance. So I can say that this is equal to 1 minus probability X1 bar does not exceed UCL or LCL given the process is in control, process in control raised to the power 2 because it's the same probability, right? And now we're pretty much done. This is equal to 1 minus probability. Saying that X1 bar does not exceed UCL or LCL, we're basically saying X1 bar is less than equal to UCL, greater than equal to LCL, given the process in control. I'm just going to say in control, raised to the power 2. Now, if you remember this term right here, we just looked at the definition of this term in a couple of slides earlier. This was, I'll tell you what this is. This is equal to 1 minus, I can write this as 1 minus probability X1 bar is greater than UCL, less than LCL, given the process is in control. I hope maybe now you can recognize this term. This term is just type 1 error for a 3 sigma control chart. So this is equal to 1 minus alpha square, sorry, 1 minus alpha whole square. I think I need to fix the square term here. It has to be outside here. And alpha, we already know for a 3 sigma control chart, this is equal to 0.0027. So you can compute and get the answer for this question, which is 0.00593. And that's how you use a given rule to compute type 1 error. Now let's look at another example. The second question is, what is the type 1 error probability using rule 2 alone? All right, let's do this then. Question number 2, let's call it alpha 2. This is equal to probability rule 2 applies. Again, I'm just using the general formula that we saw at the beginning of today's class, today's lecture. Rule 2 applies given process is truly in control. Process in control. All right, rule 2 says, if two sample means fall on the same side of the center line, we conclude the process is out of control. Okay, let's write this down. This is equal to probability both sample means lie on the same side. Lie on the same side of the center line, given the process is in control. I'm just going to say in control. Okay, now, if both sample means lie on the same side of the center line, then we can say that the probability that X1 bar is greater than center line and X2 bar is greater than center line. That is one possibility, given the process is in control. The other possibility is both of them are now below center line. So X1 bar is less than CL and X2 bar is also less than CL, given the process is in control. Okay. Now, just notice a few things. X1 bar and X2 bar are identical. So I can say the first term is X1 bar greater than CL, given the process is in control, raised to the power 2, plus probability X1 bar is less than CL, given the process is in control, raised to the power 2. Okay, let's do a little bit more work here and then we can solve this. Okay, now what do we know about X1 bar? X1 bar follows a normal distribution with mean mu0 and variance sigma square over n. And what is center line? Center line is always mu0. So now I can say that this is equal to probability X1 bar greater than mu0, given the process is in control, raised to the power 2, plus probability X1 bar less than mu0, given the process is in control. Now we don't know mu0 really, and we don't also know sigma. So what we can do is we can standardize this and we can solve. So we can do probability X1 bar minus mu0, so subtract the mean and divide by standard deviation. So sigma over square root of n is greater than 0, given the process is in control, whole square, plus we do the same thing on this side, X1 bar minus mu0 divided by sigma over square root of n. This is less than 0, given the process is in control, raised to the power 2. All right, now this term right here, these two terms, these are standard normal. So I can say this is probability z greater than 0 whole square plus probability z less than 0 whole square. And z is just a standard normal. So if you can compute these two probabilities, you'll get 0.5 for both of them. And this should be intuitive because we are really just asking the probability that if you think about a standard normal, which is a symmetric distribution, we're just asking the probability that z is greater than 0, which is 0.5, probability z less than 0, which is also 0.5. So if you add these two things together, you get the final answer as 0.5. All right, let's look at the third question. The third question is, what is the overall type 1 error probability based on the two rules, given that the two rules are independent? So now let's use these two and write down alpha 3, which is a combination of rule 1 and rule 2. In this case, your alpha total or alpha 3, this is equal to 1 minus product of I is equal to 1 to k, 1 minus alpha I. So in this case, this is equal to 1 minus alpha 1 times 1 minus alpha 2. And if you plug in alpha 1 and alpha 2, you'll get 0.5027. Right, let's look at question number 4. Question number 4 says, if the process has a mean shift of one standard deviation, one process standard deviation, what is the type 2 error probability using rule 1? Okay, so now it says that mu1 is equal to mu0 plus 1 sigma. There is a one process standard deviation shift. So this is your delta. Right? Remember, to compute type 2 error, you need to have delta. Once you have delta, you can compute type 2 error. Now we are using rule 1 in question number 4, and we're using rule 2 in question number 5. So let's look at 4. Let's call it beta 1. This is equal to probability. Now, to compute type 2 error, you basically say rule does not apply. So rule 1 does not apply given the process is out of control. Okay. Now let's write down rule 1. Rule 1 does not apply. If rule 1 does not apply and rule 1 was one or more sample means are outside the control limits. So if rule 1 does not apply, I can directly say that none of the sample means are outside the control limits. Given the process is out of control, OOC. Okay. Now this should be straightforward. This is equal to probability. None of the sample means are outside the control limit. So I can say X1 bar is less than UCL, greater than LCL, given the process is out of control, times, same thing for X2 as well, because both of them has to be inside the control limits. Now, both of them are identical, so I can just take a square here, right? Actually, let me not skip steps. So let's put it this way. Let's say X1 bar is less than UCL, greater than LCL, and X2 bar is less than UCL, greater than LCL. Okay, now we go to the next step where we say that X1 bar is less than equal to, actually, let's use less than equal to, greater than equal to LCL. Just to maintain consistency, I am putting it less than equal to. Process is OOC raised to the power 2. Now we are ready to solve this problem. This is equal to, if you remember this term right here, this is beta, this is type 2 error. So if you know beta, you can write down the answer. So beta, this beta is for a standard normal 3 sigma control chart. So beta in this case is phi of Z alpha over 2 minus delta over square root of n divided by sigma minus phi of negative Z alpha over 2 minus delta square root of n divided by sigma. This is equal to phi of Z alpha over 2 is 3 minus delta is 1 sigma. So delta gets cancelled, n is 4. So square root of n is square root of 4, which is 2, minus phi of minus 3 minus square root of 4, which will give you, this is equal to phi of 1 minus phi of minus 5. And if you compute this, you will get roughly equal to 0.84. So you go back here, plug in 0.84 square, and you get the answer. So which is 0.7. Okay. All right. Now the last question is just based on using rule 2 to identify the type 2 error. So question number 5 is, let's call it beta 2. This is equal to probability that rule 2 does not apply given the process is truly is out of control. Okay, now let's look at rule 2 one more time. Rule 2 basically says, let's go back to rule 2. Rule 2 says if two sample means fall on the same side of the center line, we conclude the process is out of control. Now, if rule 2 does not apply, it basically means that the two sample means are not on the same side. Okay, so I can write this as probability two samples are not on the same side of the center line, given the process is out of control. Process is OOC. Okay, so now let's just try to enumerate the possibilities and then we can get the answer. So we basically say here, this is equal to probability two samples are not on the same side, which means one is above, the other one is below. So let's say X1 bar is above CL and X2 bar is less than CL, given the process is out of control. And the other possibility is plus probability X1 bar is less than CL and X2 bar is greater than CL, given the process is out of control. Okay. All right. Now, you see, x1 and x2 are identically distributed. So if x1 and x2 are identically distributed, the first term and the second term are essentially the same thing, right? So if they're the same thing, we can basically just compute one of them and do twice of that. So let's see if we can compute the first term. Let's just focus on the first term here. So this term, I can say this is probability x1 bar is greater than CL given process is out of control times probability x2 bar is less than CL given the process is out of control. Now you already know this, CL is mu zero. Fine, CL is mu zero, and we encountered a similar situation in question number 2 as well. The only difference between question number 2 and this question number 5 is that earlier the process was in control, now the process is out of control. So if the process is out of control, it means that x1 bar, the distribution has changed to mu1 as opposed to mu zero. Standard deviation remains same, sigma square over n. So if I go back to question number 4 and 5, you see that it says there is a shift in the process mean of 1 standard deviation, and that mu1 is equal to mu 0 plus 1 sigma. So the process mean has shifted, and then this is mu 0 plus 1 sigma. And this is very, very important. You have to be very careful. If the process is out of control, you have to make sure that you use the right process mean. Okay. So now, knowing this, now we can solve the problem. We can standardize both the terms. Actually, let's do one more simple. Actually, no, it's fine. We can write the first term as probability x1 bar minus mu1 divided by sigma over square root of n is greater than CL is mu 0 minus mu1 divided by sigma divided by square root of n, given the process is out of control, times probability x2 bar minus mu1. Sorry, I think I lost my connection. Okay, so I'm back up again. All right, so let's do it now. This is multiplied with probability x2 bar minus mu1 divided by sigma over square root of n is less than mu 0 minus mu1 divided by sigma over square root of n. Now, hopefully you get an idea as to why I'm keeping these conditions with me, because I want to make sure that I know what is the true process mean and what is the mean and standard deviation of the quality characteristic that I'm looking at. Okay. All right, so now I can say this is probability z greater than mu 0 minus mu1 is just negative sigma, and sigma gets cancelled out, so you get negative square root of n, given OOC times probability z less than, again you get negative square root of n given the process is out of control. I can write the first term as 1 minus probability z less than negative square root of n given the process is out of control times probability z less than, actually I'm going to replace n with 4, so I get 2 OC. And then the first term is, I'm going to make this just negative 2. Now you can use your norm CDF on your calculator to compute these two terms. One more thing that I would do here is I would use my general notation. My general notation is 1 minus phi of negative 2 times phi of negative 2, right? So if you compute this term right here, let me see what you get. I don't think I have the answer right away, but give me 1 second. I can look it up. Norm CDF. Well, I know the final answer though. So, but that's not going to help us right now. Okay, so phi of -2 is 0.0228. So once we know this, I can compute 1 minus 0.228, which will give us 0.9772 times this, which is equal to 0.2228. Okay, so we have got one of these terms. If you remember, we still have the second term, but what we know about the second term is this term. What we know about the second term is that it is same as the first term because x1 and x2 are identically distributed with each other. Right? I know the signs are flipped, but that doesn't matter because x1 and x2 are identical to each other. Right? So your final probability beta 2 will be equal to 2 times 0.0228, which gives you 0.0445. All right. And that's the end of all the 5 problems. Now, this is a little bit involved, so I would strongly encourage you to practice this on your own. And if you have any questions, come and see me during the office hours. All right, now let's look at a couple of things. This is not very important, but I've mentioned a couple of factors that you can identify as potential causes to when the process goes out of control. Okay, so and then there are some patterns that you can actually see in control charts. One of the patterns that we typically talk about is you might see high proportion of points near the outer limits. What it basically says is that you can actually have a control chart that looks sort of like this. This is UCL, this is LCL, and you might observe a bunch of points jumping around here, and then all of a sudden it will go somewhere here, come down here, 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 right? These lines don't really mean anything. I'm just trying to trace my points. But you notice something interesting here. There are points clustered near the control limits, right? And this type of condition happens when you have a mixture of 2 different quality of materials. You know, one of these clusters, maybe the top one will represent one of the quality, one of the type of products that you're using, and then the other could represent the other quality of product that you're using, right? And so this also happens when you have mixture of materials of different quality. Maybe the top one belongs to one quality, the bottom one belongs to another quality, right? This can also happen because of improper subgrouping, so that should also be taken care of. And in many cases, we also notice a pattern, something called stratification. Stratification happens when most of the variability in the process is just limited to the center line. So it will oscillate just around this point. And this is called stratification. This could happen because of multiple reasons. The first reason is that maybe your control limits are too broad, too wide. They're not properly computed. And the second problem that can happen is systematic sampling. This is where you try to over control the process, right? You try to remove any of the samples that deviate a little bit too much, right? That's probably not a good idea in quality control. Okay, and then the book also has a bunch of other patterns and causes. We are not that concerned about that in this course because these are mostly observational, right? That's why we don't discuss this much in a statistical quality control, but you can always go back to the book and read more about this. All right, now moving on to the last topic of this chapter, which is the performance of a control chart. Now, so far we have looked into type 1 and type 2 errors. We have looked at different ways of computing type 1 and type 2 errors, and we've got good understanding about type 1 and type 2 errors. The problem with type 1 and type 2 errors is that they are a little bit less intuitive. Imagine going to an operator and saying that, can you control the process so that the process leads to a type 1 error of 0.009925? Well, that does not immediately give any intuition. And so to develop some intuition, people developed a method that's called average run length. And that's very much related to type 1 and type 2 error, right? It's actually computed from type 1 and type 2 error, but it has a lot more significance and meaning than type 1 and type 2 error. Right, so to understand average run length, we'll start with run length. Okay, so run length is basically number of samples plotted plotted inside the control limits on or before an OOC sample, an out of control sample is observed. Okay, so let's look at an example. Imagine you have a control chart, and then you have some, let's say, central line, you have UCL, you have LCL. Okay, now let's say you're observing some data points. Let's say this is the first data point, second data point, third data point. All of these are inside. Fourth one is inside, fifth is inside, sixth is inside, seven is inside, and then the eighth one is outside. So in this case, your run length is 8. It's on or before an OOC sample is observed. So that gives you a run length of 8 in this case. Now, problem with run length is that it's a random variable. Every single time you start monitoring a process, every single time it will go out of control, or the first out of control sample will be plotted at a different time. Maybe sometimes it might be plotted on the 100th sample. Maybe it will be plotted in the second sample or the third sample or 1,000 samples, right? Because of this variability in the measurements that we're observing, the run length is also variable. So what we do instead is we compute something called average run length, which is basically the expected value of run length. Okay, now let's try to understand what is this expected value really means. Now you can compute run length when your process is in control. You can compute your run length when the process is out of control. When the process is in control, we call average run length 0. This is when process is in control. And let's try to understand what this actually means. ARL 0, by definition, this is the average number of samples plotted on or before an OOC sample is observed given the process is in control. The process is in control. Now, we talked about this a little bit earlier, that even if the process is in control, there's still some likelihood that you might observe 1 or 2 points outside the control limits, just by the virtue of the variability in the process. And this we called as type 1 error, right? Probability of observing an out of control situation, even though the process is in control. Now, what it really means is that, let's take an example to understand what it really means. Let's say ARL 0 is equal to 1,000. So if ARL 0 is 1,000, then we are going to observe on an average 1,000 samples before one out of control sample is observed. Now, all of these discussions are happening in average, okay? So it might be a little bit different every single time, but on average, for every 1,000 samples that I'm going to plot, I will observe 1 out of control samples. Right, now think about 3 different scenarios. Let's say ARL 0 equals to 10, 1,000, and 10,000. So in the first case, we're going to observe on an average 1 out of control sample for every 10 in control samples plotted. In the second one, we're going to observe 1 out of control sample on average for every 1,000 samples plotted. And in the third one, we're going to observe 1 out of control sample for 10,000 samples that I've plotted. So you can see clearly here, we would always prefer to have the higher value of ARL0, right? Because we want fewer and fewer out of control samples when the process is in control, right? So this is preferred as higher the better. And you can also think about this as a false alarm, right? So consider the 10,000 example. In the 10,000 example, we are basically saying that we will have 1 false alarm for every 10,000 data points monitored, right? Which is great as compared to 10, where you'll observe 1 false alarm for every 10 samples observed. Right, so I hope that gave you an idea about average run length 0. Now let's talk about average run length for the out of control process. And when the process is out of control, we call it ARL1, which is process is out of control. Right? Now in this case, let's define this again. This is the average number of samples plotted on or before an out of control sample is observed when the process is out of control. Now this time the process is out of control. Let's look at an example again. Let's say ARL1 is equal to 10. So it basically says that when the process is out of control, so something wrong has happened, I would still plot on average 10 sample points inside the control limits, right? I would still plot on an average 10 samples inside the control limits before an out of control sample is observed. So in other words, it is saying that I'm still going to wait for collecting 10 data points before an out of control situation is observed. Now think about it this way. If I have an ARL1 of 1, 10, and 100, in the first case, we are saying that when the process goes out of control, I'm going to observe just 1 single in control sample before an out of control sample is observed. In the second one, we are saying that when the process goes out of control, I'm still going to observe 10 sample points inside the control limits before an out of control sample is observed. And in the third case, it is saying that I'm going to observe 100 in control points after the process has gone out of control before an out of control sample is observed. So you can clearly see that I would prefer ARL1 equals to 1 because ARL1 is kind of like an average detection delay. ARL1 equals to 1 means I have to wait for just 1 sample before an out of control situation is observed. ARL10 means ARL1 equals to 10 means I have to wait for 10 sample points. And similarly, ARL1 equals to 100 means I have to wait for 100 sample points. I have to wait for 100 sample points before an out of control situation is observed. So you can clearly see we want ARL1 to be smaller, and smaller, the better. And this ARL1, this is nothing but average detection delay. And I would want to go back and say that ARL0, this was the false alarms, number of false alarms. Right, now, how do we compute them? Computation of these two are very simple. ARL0 is simply 1 over alpha, right? So now you can actually think for a 3 sigma control chart, alpha is equal to 0.0027. So your ARL0 is equal to roughly 370. Now 370 is a unique number because if most of the control charts are 3 sigma control chart, then ARL0 is always fixed to 370. Now it basically means that for every 370 in control samples you have plotted, on average, you're going to observe 1 out of control situation given the process is in control, which is not bad, right? Observing 1 out of control out of 130 or out of 370 is okay, is acceptable. And that's the discussion that I'm trying to do here as well. All right, now let's move on to ARL1. ARL1 is equal to 1 over 1 minus beta, okay? Where beta is type 2 error. And keep in mind, we want to reduce beta always. Beta is type 2 error, right? So as beta decreases, ARL1 also decreases, right? Well, there's a 1-to-1 correspondence between ARL1 and beta. All right, now before we close this chapter and this lecture, let's solve one problem here. Suppose that an X bar control chart with 3 sigma limits and n equals to 4 is used to control a process. Assume the process mean is changed by 1 standard deviation. So there's a shift in the process mean. Mu1 is equal to mu0 plus 1 sigma. And Z alpha over 2 is given to you as 3 and n is equal to 4. Okay, so the first question is, what is the probability of detecting a change by the first sample after the shift? So the question is asking us probability of detecting the shift or the change. It's the same thing. Detecting the shift by the first sample, by the first sample after the shift, given the process is out of control. Because there is a shift, the process is already out of control, right? Now detecting the shift. Now, any control chart would detect a shift by plotting a sample which is outside the control limits, right? That's how you detect a shift. If it still stays inside the control limits, you would never detect the shift, right? So in this case, I can say probability that X bar is greater than UCL, less than LCL, given the process is out of control. That's when you detect the shift. I can rewrite this as equal to 1 minus probability X bar is less than equal to UCL, greater than equal to LCL, given the process is out of control. And you know this term. This term is beta, right? And we can compute beta. Beta is equal to phi of Z alpha over 2, which is 3 minus delta is 1, square root of n is 4, divided by sigma is what? Actually, shift is 1 sigma. So shift is 1 sigma divided by sigma minus phi of -3, -2. So this gives you roughly 0.84. And then you get the answer to the first problem as 1 minus 0.84, which is equal to 0.16. Right? And then the next question is, what is the probability of detecting the change before collecting the 5th sample? So in this case, it is asking me to do probability of detecting the shift or the change before collecting the 5th sample, given the process is out of control, right? Now I can say that probability of detecting the change before collecting the 5th sample is essentially maybe your first sample can detect the shift, or maybe the first would not detect, the second can detect, maybe the first 2 cannot detect, third can detect, maybe the first 3 cannot detect, the 4th can detect. Now I can see there are multiple possibilities here. So I'm going to avoid all the complexity and just say that 1 minus probability not detecting the shift or the change until the fourth sample, until the fourth sample given OOC. Now I can say that if the shift is not detected by the fourth sample or until the fourth sample, that basically means that the shift was not detected by the first one, it was not detected by the second one, it was not detected by the third one, it was not detected by the fourth one. So I can say not detected by the first sample given OOC. And since all of my samples are IID, I can just raise this to the power 4. And then this will be equal to 1 minus beta raised to the power 4. You already know beta. So let me see if I can quickly compute the final answer. 1 minus 0.84 raised to the power 4, which gives us roughly 0.502. Right? And then the last question is, what is the average number of points plotted on the chart until a signal is observed? When you say a signal is observed, it basically means until an OOC sample is plotted. Sample is plotted, right? And that's basically the definition of ARL1, average run length. Average run length is the average number of points plotted on the chart until an OOC signal or OOC sample is observed. So in this case, I can compute my ARL1 is equal to 1 over 1 minus beta. We already know beta. Beta is 0.84. Plug it in, you'll get roughly 6.25. So it means on an average, you have to wait for 6.25 samples to plot on the control chart inside the control limits until an out of control sample is plotted. All right, so I'm going to stop here. I think this is a good ending to chapter number 4. There are a few other things that I mentioned in this chapter. These are not really important, but if you want, you can review them, and you can also go back and read through the book. But this is, again, not necessary. All right, thank you very much. I'll see you guys later. Bye.